We are now ready to confront probably the most important function in all of modern cryptography. This is a famous function called Euler's Phi function, and it is going to be incredibly important for everything we do this semester and for anything you do in later coursework. If you're a cyber major in any sort of actual modern cryptography, the Euler Phi function will definitely matter. So, to motivate this a little bit, uh, let's talk about something we discussed in the last lecture, which is if you want to work mod n, the question is how many affine keys do you have when you work mod n? And we saw that a main ingredient to answer that question is to know how many invertible elements you have mod n. So if you're working mod n, you would need to know how many elements mod n are actually invertible. Okay, that's one of the ingredients in answering the question of how many affine keys you have. So, for example, we already know, we've known this for a while now, that there are 12 invertible elements mod 26. And you learned on the last handout there are only 4 invertible elements mod 10. Okay? But what if you are working mod, I don't know, 52,781,925,441? How could you feasibly work out how many elements are invertible? Okay, so this question of how many elements mod n are invertible is so incredibly important that it gets its own name. All right, the answer to this question gets its own name and it's a function. Okay, this is known as the Euler Phi function. And here it is. It's simply the answer to the question. Let n be an integer, and we define phi of n. So when you plug in n, you get back a value phi of n, and that value is going to be the number of invertible elements mod n, and that's it. Okay, so phi of n is just a shorthand for how many elements mod n do I have that are invertible, and that's it. Now, on the last handout, you learned how to calculate phi of n, at least in principle. Okay, we know that an element is invertible mod n if and only if it's relatively prime to n. So the GCD has to be 1. Okay, so what you would do, just like last time, is you would make a table for the inputs 1, 2, 3, all the way up to n minus 1. You would then use, in principle, the Euclidean algorithm to compute the GCD, and then simply count how many times you get a 1 as the answer. How many 1s do I get as an answer there? And that's what we did last time. So let's do that a few more times just to get familiar with calculating outputs of the Euler Phi function. So for example 1 here, let's compute phi of 6, okay? That's the question of how many units do we have when we work mod 6. So if you work mod 6, you know you have elements 0, 1, 2, 3, 4, 5. Okay? Now, 0 is never going to be invertible, so I never bother to check it. And so what you really do is you check 1, 2, 3, 4, 5. You check the GCD of each one of those guys against 6, right? So 1 is 1, 2 is 2, 3 is 3, 4 is 2, right? The GCD of 4 and 6 is 2. They both share a 2. And 5 is 1. And so I get a yes there and a yes there. So I only have 2 yeses. I have 2 spots where the GCD is 1. And so since I only have 2 yeses, the answer is that phi of 6 is equal to 2. Right? So phi of 6 is 2. Let's try that again with phi of 7. Okay, so we work mod 7. I'm sorry, there's a typo right there. Sorry, typo. That should be a 7. When you work mod 7, you have elements 0, 1, 2, 3, 4, 5, 6. Okay? So here's a table that you have. You have the elements 1, 2, 3, 4, 5, 6. I'm not checking 0. You take the GCD of each one of these against 7. All right? But 1 and 7 is 7, and 2 and 7 don't share anything, and 3 and 7 don't share anything. None of these guys share anything with 7. And so every single answer you got here was a 1. Look at that. So you have 6 yeses here. And so phi of 7 is 6. That should be interesting because that didn't happen before, okay? Do you notice what just happened? Why in the world is phi of 7 6, which is so much bigger than phi of 6, which is 2? It's just 3 times as big as the answer here. This was a 2, that was a 6. That's impressive, and as you might guess, it has something to do with 7 being prime, right? And it does, okay? So let's do a couple more, and we'll take a break and finish this handout here. So what I want you to do for the first question on the Canvas quiz is do this tabular method right here to compute phi of 8. All right, so do this tabular method to compute phi of 8. Okay, as one final example here, let's compute phi of 9. Okay, so when I work mod 9, I'm going to have elements 0 through 8, and if you just look at the table here, check my math, almost everybody is relatively prime except for 3 and 6. 3 and 6, there's your 3, there's your 6. They both share a 3 with 9. So if you count the number of yeses, you get 6 yeses. And so phi of 9 is equal to 6. Okay? So that's the idea of the Euler Phi function. So what I've done here, just for fun, is I've given you a table of summary values just for phi of n going for no good reason, just going 1 to 17. Okay? So here's the values of the Euler Phi function from 1 to 17. I have left out 8 because you're supposed to do it in the Canvas quiz. But if you just look at the outcomes here, notice how chaotic the outcomes are, right? Here's the second row of outcomes, right? There appears to be no pattern in the outputs. They jump around all over the place. It's sort of 1, 1, 2, 2, 4, but then it drops to 2, and then it jumps to 6, and then later on it drops to 10, and then it jumps to 4, then it jumps to 10, drops to 4, and then it jumps to 12, but then it drops to 6, and then an 8 and 8, and then it suddenly doubles to 16. So there's not a lot of patterns here in the outcomes, and it ends up that that's a fact, actually. There are actually no patterns to the outputs in the Euler Phi function. They sort of jump around all over the place. And indeed, this is why the Euler Phi function is so useful in crypto. It turns out that because the outputs jump around so much, it's incredibly hard for Eve to guess anything about the outputs. And so if Alice and Bob are sharing a secret about the outputs, they can hide that from Eve and do some crypto. Okay? So for the second exercise, I want you to do the tabular method just to get the next entry in the table that I didn't do for you, which is what is phi of 18. Just to give yourself one more entry in the table. Just do the GCD method there. Okay? Now I'm going to take a break here in a second, and what we're going to do in the last half of this handout is get realistic, because this technique of just computing the GCD for everything is not going to work. For instance, how would you calculate something like phi of 115? Or how about phi of 5,461? Are you really going to sit there and write out everything mod 5,461? That would be 5,460 things to check. That would be you running the Euclidean algorithm 5,460 times and then going back when you're done and counting the number of ones. Is that really going to work? It's not likely to be very feasible for large numbers, okay? So let's take a break and we'll come back and see if there's another way to do this. It might be a little bit slicker. The answer is yes. Stay tuned.